amenable to any working concept of life. Machines can have fixed blueprints. Active, self-directed entities, such as organisms, cannot, at least not in any received sense of what the term blueprint has come to mean. Design must invent new approaches besides the fixed template or blueprint. And indeed, it has, in many fields, already begun to do so. Thanks to the computer and the interactive cathode ray tube, most scientific fields are already enjoying some success, more in any case than in architecture. Why? Now there are well, actually, to tell you the truth, I wrote this before before the architects started to speak, the next section, and I really did not expect to be so stunned, to tell you the truth, with some of the work. But in any case, I think that there may still be, certainly I know from being in the schools, there still is a tendency to approach, as Jeffrey said, an entirely new problem in a rather old way, and what I really want to argue here today is that, as Jeff had already mentioned, there need to be new ways, new approaches, and new languages, let's say, of understanding. Now, there are essentially three domains, and this is really, I suppose, my argument today, in which one can approach complexity. There is, first of all, the wet complexity of the real world. This is the most compressed and embedded form of complexity. It is live and real and material, but it is so manifoldly entailed that it is difficult analytically to extract without recourse either to reductionist techniques that in the end will kill it, or to archaic empirical techniques whose virtues I'll leave for another occasion to expound. The forms of our real world, in fact, present iconic examples or images of complexity that are apprehensible without any particularly nuanced understanding of the dynamical processes that produced them. Complexity, in a sense, it's not an image, but it's rather a certain way in which events are ordered and nested within one another, which is why I actually like that term that Jenks used of, I think it was deep organization or organizational depth or something like that. Now, really what I'm criticizing here is the idea of adopting simple biomorphic forms as it was done in the painting of the 1940s and 50s. The second domain of complexity is in the analytical, semi-abstract domain of modeling tools. This is essentially a graphic language of geometrical figures that represent isolated interactions of grouped elements, attractor reconstructions, topological models, fitness landscapes, etc. These are essentially sexy, highly suggestive images, complex or living, but only formed organisms are. Now let me explain. It is not enough simply for an encoded message or form to be transmitted successfully and accurately from one milieu to another in order for it to be said that a living process, a complex process, has occurred. If it were so, we would say that self-replicating crystals were alive. But we don't. We don't say that they're alive for the simple reason that all that has occurred in crystal replication is a rote transmission of genetic information. There has been no active transformation or incorporation of the surroundings or the environment that would result in a collaborative formation of an active or metabolic shape, that is, a phenotype. So really, the concentration really must go toward the shapes, the forms, and the phenotypes. Now, for this reason, I think I did something absolutely brilliant here, and I think I've actually just dropped that 6 or 7 pages without even trying. Well, it's your luck. Well, here's the story. I mean, yeah, reconstruct. Where's that attractor? Where the hell is that? No, the reason to lament it is just that I wanted to set up a future discussion with Charles about Romanticism. because it was all about Goethe. They are gone. There's an emergent property. Now, may I break with decorum and, like, scan my... Is it in my bag? I mean, it might be in my bag. Let's... I'm willing to give it up, to tell you the truth, but...
This is like public art.
You're out of luck. I can't believe that. That was beautifully done, actually. It was a smooth transition. Now, that is catastrophe theory at its best. Let's go back a little from the Waddington. Okay, well, look, I was, among the other things that surprised me yesterday, now am I going to get this in order now, is that Goodwin, I was surprised by Goodwin's mention of three philosophers, rather offhandedly in his presentation. The first was Kant, the second was Goethe, and the third was Whitehead. I would love to talk about Whitehead, but I'm incapable of doing so. So I'm going to talk about the other two. The extraordinary thing, of course, is that when he mentioned them, one could actually feel the pull, and I really believe this, the pull of ideas actually directing themselves to one another, in the sense that people who work on similar things, it's bizarre. It's a little bit like the bugs that find the grass. And in this case, I mean, we are clearly the bugs, and the grass is Goethe. And I was really shocked to hear that, you know, Goethe, Kant, and others. But now, anyone attempting to think the problem of organism will, it seems to me, will at least encounter the slope that moves in that direction. But I was especially interested in his recitation of the famous passage from Kant, where Kant denies the possibility of that there will ever be a Newtonian explanation of of life processes, because it reminded me of a beautiful little book by Ernst Cassirer called Rousseau, Kant, Goethe, in which Cassirer makes one of those sweeping and brilliant condensations of which he is so famous, of a huge set of intellectual processes, and condenses them into a single. That's the only reason I can remember it, actually. Now, in that book, Cassirer claims that Goethe's scientific writings complete the transition, get this, it's so beautiful, from the generic view to the genetic view of organic nature. Now, it's a very memorable formulation, but what does it mean? By generic, he of course was referring to the Linnaeus and the Linnaean view ordering system of in biology or in natural history, the classification and taxonomy of which we spoke so much of yesterday, where you subordinate the multiplicity of nature to a kind of grid, a rational grid or tables of concepts. The divisions, of course, into species and genera, which is where Cassirer gets the concept of the generic, orders, classes, families, etc. The Linnaean generic version stresses constancy. And what he, of course, is claiming, Cassirer, if I remember it, is that in Goethe, what we find in the genetic view is something that stresses changeability. The new Goethean view, Cassirer argues, states that to understand nature, we must grasp more than just its products. One must grasp the process of life. And this must be sought, and this is very important, and this is where Goethe's Kantianism comes in, it must be sought in abstract, formative principles. We could go, I mean, you know, we could go on and talk about the problem of the schema in Goethe in relation to some of the comments that Greg made regarding the analysis of Colin Rowe, but maybe we'll do that later. Now, this is exactly what Goethe does. First, by introducing, for the very first time ever, the concept of morphology. Now, you've probably all heard about that basically is Goethe's concept. And second, because he nests the concept of morphology. He nests this new form science within a dynamic field of transformation, what he calls metamorphose or metamorphosis. And third, by supplying the first example of a dynamical genetic theory. I don't, of course, mean DNA because it didn't exist. It was not even a glimmer in whoever's eye at the time. The first example of genetic theory using interactive algorithms, and that's really what I want to insist on, even though I did present it a little bit a few months ago when I was here. Now, it's precisely these latter developments that Cassirer is identifying when he claims that in Goethe, a new ideal of knowledge was created here at this end of the 18th and beginning of the 19th century. Now, how does algorithmic complexity function in Goethe's system? First of all, I would claim he was the first to look at a plant in and as a morphogenetic field. Now, how does he do this? I hope, well, anyway. He introduces three elements. The first is the introduction of the type concept, okay, which the type in this case is leaf. Everything is leaf in the plant, he argues. I think it's an extremely misunderstood concept in Goethe, based especially on some of the conversations I heard over dinner the last couple of nights. But it is, yes, an type, an archetype. He called it the Urpflanze, and everybody knows about his wandering around in the forests, actually at some point looking for this arche plant. But no, there is nothing explicitly metaphysical about it at all. It is not a thing that exists, but it's rather a logical matrix, an abstract generating form, okay? It never appears as such in this sort of so-called ideal state, but it is always manifested as a variant, okay? And it never needs to be manifested in any other way but as variant. Think, for example, of the human face. Every face is different, and the parameters of, size of jaw, how far apart the eyes are, even whether you have two eyes, you still recognize it as a face. Essentially, nobody would claim here that there is there is an Ur face. Somehow, it's the schema of face-ness. Number two, he introduces a second element, which of course begins to get everything moving. There's the addition of an open gradient, okay, which is really just a gradient of progressive refinement of sap. Essentially, you have the movement from crude to refined, and then there's this process of drainage, etc., and so there's a filtering gradient going on. Number three, the third element, is the addition of a closed cycle, okay, somewhat in opposition to the concept of the open gradient. The closed cycle is really just this. In a plant, there are waves of expansion and contraction which occur in time, okay, and they correspond to the different stages of the plant's life, which also have corresponding morphologies. The first stage is the vegetative stage, the second the blossoming, third the bearing of fruit, and who knows, there's seeding, etc. This is opposed to the, in some ways, this temporal cyclical one is opposed to the purely spatial gradient of element number two. Now, how does this all work together to form an algorithmic complex system? Element number one, which is the element of type, essentially introduces something that today we would call a basin of constraints. Essentially what it does is it establishes general rules, parameters, a kind of set of structural givens. Okay, now the leaf concept appears, if you like, in the plant life as a series of beats. Basically what it does is it imposes a general set of information down every time the plant, you can think of it almost like, in Boolean networks, there are different I can't remember what those are called, but every time it changes state is a different, I don't know what you call it, different stage. Okay, you have the basin of constraints, which is introduced by type. Number two, the second element, the element of the gradient, it actually introduces directionality. Okay, directionality into the system. It produces what we would call today a symmetry break and a flow space of constant change. That's to say, remember from the gradient that moves from less refined to more refined sap. And a perpetual difference or differentiating engine, let's say, and thus uniqueness. Okay, every moment, thanks to this gradient, is actually unique, and every point is actually unique to a certain degree, which gives us that necessary detachability that one needs, the detachability of events and structures. And here, finally, so process 2, one could say, it actually operates on and begins to deform process 1, which is the continual, regular beats of the information that imparted by the type form. Third, the cycle, the expansion-contraction cycle, what it does is it introduces repeatability. This provides, and this is kind of important because it's hard to grasp, it provides a flexible ground structure, a kind of background, a regularity, let's say, a regular recurrent macro process, an envelope, let's say, that lends a law-like structure to the profusion of pure uniqueness that was generated in process number 2, in the directionality. Repeatability punctuates and gives intelligibility to a process that unfolds in time. In a way, it gives it place. It gives a stability envelope for radical instabilities that generate, in number 2, unbridled or open-ended change and novelty in that second process. And finally, it introduces the multiplicity of simultaneous temporalities, which is in fact, of simultaneous of different temporal unfoldings, which characterize all complex systems. Now, one could go on, one could add in, the system is actually a little more complicated than that, because he has the concept of centrifugality, where the type actually, as an information type, it actually moves from an inner core and spreads outward, whereas there's a second gradient which moves from the outside, which is the environment, actually presses from outward inward, so it operates externally and creates a kind of a conflict regime very similar to the types we see in chemical reactors, in diffusion systems, etc. Now, that is not even so important because the 3 principles are enough. But the important thing here now in the Goethean system, this very simple algorithmic system, and by the way, it has long been claimed that Goethe's botany is profoundly interesting, but wrong. Now, really creative biologists have never given up the Goethean model. And I just found out last night, having dinner with Brian Goodwin, that since 1991, they've discovered that Goethe was in fact right. They found a homeotic gene which actually controls expression of the leaf form, meaning the DNA actually does have recourse to a repeated data bank that it continually expresses in relationship to another set of moving elements, and it comes out differently. I asked him, I said, can you actually get a petal to be expressed, near the base of a plant, or even down at the roots? And he said, yes. And I said, I bet you got pictures. And he said, yes, I'll send them to you. So one day I may do a presentation, and there will be images, and we'll see all kinds of deformed plants the way we saw all those deformed hands, which I think are pretty fabulous, actually. For example, in the stuff that Greg, posable thumbs, but no, but Greg makes an interesting point. He says, oh my God, I'm showing this stuff, that's all out of date. But in fact, nothing is out of date. If a good geneticist always have good ideas, and good ideas, even if they prove not to be the way nature solved them, are always up to date. So, I think, pillaging history for good ideas, there's absolutely nothing wrong with that. Now, number 1, back to number 1. The organism, according to Goethe, is the expression of the interaction of multiple systems of rules or mutually modifiable instructions. That's essentially what I want to argue here. This is where the complexity comes from, the complexity from algorithms. B, each of these individual systems of rules represents different scales of shape pressures and different rates of unfolding, creating a bona fide complex and polyphonic structure with perpetual crosstalk between the strata, possibly, at least one could speculate, the source of their stability as organisms. And C, rules are not blueprints, but engines. They are not just unfolded, but are perpetually read out in continually varying situations and under continually varying conditions. Rules are like moving basins or templates, limiting development within parameters, but encouraging infinite variation within those parameters. enormous freedom emerges once variations are allowed to interact with other variations. Amazing flexibility arises, and the possibility space of the system mushrooms astronomically. And of course, the great example in biological science is the Cambrian explosion, where there was a proliferation of new body plans. And of course, this seems to happen according to the Eldridge-Gould model, and they call it punctuated equilibrium. There are these explosions where there's these proliferations. Goethe's botany essentially is, in pure classic complexity theory formulation, 3 simple rules generating infinitely complex forms in infinite profusion. Now, my final comments, we're going to go back. We're going to circle back to that Waddington stuff I just did. Will be to reintroduce the material, a little bit of the material that I gave in my lecture here last February with Waddington. But I'm not going to show you pictures this time. I'm just going to describe it. Because of lack of time, of course, I'm going to have to be brief and deform a very elaborate, I think, and very elegant system devised by Conrad Waddington, who incidentally was Goodwin's teacher, at around the mid-century. Now, I may make everything sound as if it actually came from Goethe. It doesn't. But the important thing is for me to show that there's the same algorithmic principles operate, that they actually generate a specific type of space, and that there is, in fact, well, at least one can hint at exactly what type of forms actually develop in this kind of space and what they might look like. Okay, so here's really the question is, again, to repeat that page 18 that turned up out of nowhere. What is the source of stability in biological organisms, and what could be the source of stability in designed forms, as opposed to forms which actually happen on their own and are the result of extremely unknowable conditions? So I mentioned the thing about Goodwin's insistence on the phenotype and the form. The crystal replication is not equivalent, of course, to a description of life. Okay, now Waddington, I don't know if I mentioned this, Waddington always preferred to make a distinction between inert information and what he called instructions, which he understood to be dynamic instructions or programs. Now what Waddington called instructions are precisely what I'm calling algorithms. Now you might remember an image I showed. People tend not to forget this image, and that's one of the reasons I don't want to show it. Not around Kipnis. Now you may remember an image that I showed of that undulating surface. I'm going to describe this a little bit with my hands, just for those who weren't here. That it's kind of like this undulating surface, which was sort of like a taut tarpaulin, held down to, but actually hovering well above another, this time rigid, planar surface by an array of interconnected guy ropes and anchored to pegs on the lower surface. So you have the rigid flat plane above, and you have the undulating taut plane above connected by guy ropes. One of the major points that I tried to make last February was to show how there could never be an exact correspondence between the original transmitted message, that is the DNA, and the phenotype, that which is produced when the genotype is used as instructions to assemble the form. Now, 2 general categories of deformation intervene here. The first is one from the environment, which the environment continually funnels its own shifting information into the system, either as serendipitous accidents or as systematic selection pressures. You see, the system computes and actually builds the environment just as much as it builds itself or expresses its genotype. Goodwin actually, at dinner again last night, actually suggested, and I know he does hold down the left-wing position on this question, actually argues that it's more like 99-1, that the genetic information actually only determine about 1% of these of phenotypic forms. And the second source of perturbation source of pollution, let's say, of the data, comes from the complex interaction of individual genes in coordinated blocks, that is, the interaction of instructions. and interaction of their chemical products, evocators, regulators, triggers, inhibitors, and all that stuff. Now, what I'm describing here is how the system moves from genetic space below, how it moves into the phenotype space, the form space, above, by passing through epigenetic space, or the space of developmental processes. But the real question is this: what keeps things from going absolutely haywire in the process when it gets into that unstable middle realm? Well, there's a stabilizing feature here that is buried deep within the complexity of the system. It is known as canalization, or regulation. Now, these terms reflect an important but almost perennially overlooked feature of living or dynamical systems. That when dynamical systems are adventuring far from their attractors, their stability is a mobile one. In mathematical terms, one would say that they are not stable around a constant value, but rather around a particular course of change in time. Now, the emphasis here I want to put on the word course. Waddington coined a new term to describe this new mobile, stable state. He called it HomeoResis, an adaptation of the better-known term homeostasis, with rhesis coming from the Greek word rheo, which means to flow. He compared HomeoResis to a stream running down a valley bottom, or a ball coursing down the topography of the undulating tarp, which I just described, except on the top side. Now, you can deflect or perturb the ball or the stream of water, and the system will not even try to return the ball or the water to its pre-inflected state, which is really the most important thing here, but rather will return it to a later point in the course, which is down the stream bed, for example, where the ball or stream would have passed later, even without the perturbation interruption. Now, what I've been calling a course, Waddington named a creod, and which he saw as a type of stabilized time trajectory. In effect, creods constitute guided pockets within which forms develop, within which forms are generated, and they are generated complexly, if you'll pardon the expression, by instructions, and especially interactions of instructions originating in the encoded blueprint. According to Waddington and the followers of his school, these creods are the single most important features of developing systems. And this is a very amazing assertion, actually, because he says that genetics generate creods, not organisms. But even more interesting, he seems to argue that this is all that DNA really does. It produces a creotic space. All the rest of morphological development takes place as a result of the interaction of the flow of an element, of the ball or of water, through these spaces, responding freely to environmental pressures and other exogenous, that's to say, coming from outside, geometrical influences. Now, geometrical influences is literally what I mean, but it's important to understand that chemical processes, which play the primary role in morphogenesis, are actually geometrical when they're modeled in phase space. And of course, even like, for example, as we saw in the Belousov-Zhabotinsky reactions, chemicals allowed to diffuse through a medium actually do produce geometries. In fact, if one studies the Turing paper on how the leopard gets its spots, one will see a direct example of a reading out by the melanocytes of the chemical space. Now, what is more, epigenetic space contains a great number of creods through which a shape or organism passes. But this space itself is also susceptible to permanent deformations, should a strong enough pressure be placed on it for a long enough period of time. In other words, the mixture of instructions pushing upwards will relent and absorb the perturbation coming from above, passing it back down into the DNA blueprint to be encoded as an adaptation. Creods, which is really the concept I wanted to put on the table today, creods are highly stable but elastic, as well as fundamentally intelligent. Now, creods are elastic courses in space, pockets or kind of petri dishes in which forms develop. But they are shapes as well. Or rather, they are the visible, I insist on that, visible immaterial courses that direct shape formation. In fact, they may be described, if you're crazy like me in a way, I mean, you describe them as mega shapes, possessing a kind of morphological persistence of vision. And what I mean by that is persistence of vision, in case you don't immediately get a sense of what that means, is essentially it's when an image sort of remains either in the brain or on the retina after the object has actually been taken away. It's a kind of an after image. Now, creotic pressure is highly available to intuition. I really want to insist on that. Complex forms generally appear simple, and I think it's important that we understand that. They are literally pinched off sections of creods, where and the reason they're simple is because most of the work, most of that algorithmic work, is actually done beneath them. Now, one way of understanding this is to think of how tonality, or key, marks and organizes a musical composition from a certain type of depth within the organizational system. Imagine especially how deep it can seem, for example, in an atonal work, while still remaining very rigorously operative. But this is not the best example to give, because it makes the creotic resonance sound as if it were something obscure. It is not. It is visible, and it can be built. Everyone in this room has seen it. I know that I have. But I do not think it necessary or fair to the brilliant images and somehow the brilliant presentation of images that we have seen in the last couple of days to go on attempting a discursive description of it today. And I will cut off there. Thank you.
Questions, baby.
Three kinds of complexity. Let me get it straight. Three kinds of complexity.
And
What was the first one? Liquid, dynamic, algorithmic, and then algorithmic is
type,
Got it.
gradients.
No, I got it. I got it.
Jesus, you're very good. You can just get up there and like sort of
There. Okay.
Thank you.
We're doing that up here. Triangle is exactly what you said. Triangle is exactly what that is. It's just a set of rules.
I know, but that's hard. Just get them to interact.
Yes. Yeah. I'm sorry. Are there questions for Sanford?
Yeah. What I don't understand, Sanford.
Wait a minute, you have a question for me?
Yes. What I didn't understand about your lecture is each one of the real scientists used graphic material to help us with very complex work, and it's like a kind of graphic symbols and outlines. Don't you think you would have been helped to do the same kind of thing?
No.
Why?
Well, I think that
Question is, why didn't he show slides?
Not slides. No.
no.
No, not slides. I meant those little
Oh,
things
yes.
with outline material.
Absolutely.
I didn't mean slides. I meant those sheets.
Transparency.
there is no question about it. I regret more than anything else not doing that. And listen, I did that once in my life in a lecture, and it went over like you have no idea. It was like a football game. And it was excellent, yes. No, I regret not having done so. As you know, I was scrambling to mark these comments down. I had 3 sheets of transparent paper, of acetate. Peter, I will never go in front of an audience with this type of material again without that exciting
I think it's clear from this conference, among all the other information we learned, that slides are out and overhead transparency.
overheads all the way. I learned that at a conference.
Especially with science.
Yeah. Oh yeah, deep science and beyond.
Any other questions? Any questions from over here? I'm going to start over here. Okay. Go ahead.
I'm interested in the concept of the new science. In the past, we talk about the theories of maybe people like Galileo, the Big Bang theory or the Darwin theory, and
I didn't get those names.
Darwin.
so like we hear about the theories, the past science theories of Darwin or the Big Bang Theory or, Pythagoras or whatever. And those have been with us and they help us to develop the world as we live in today. What I don't understand about the new science is what's the fundamental principle behind it? And if there is any, how do we foresee it as shaping the world in the future?
I have a terrible feeling that... No, I know the question. No, listen, I don't have trouble with the question. I have trouble with having to answer something so big. Were you here yesterday, by the way? Oh, no, because we sort of we all chipped in and tried to answer this question, all of us over these 2 days. You're really asking what you want to do a summary? What is at stake?
Question. What is the new science and how will it change the world?
I don't believe that is. Look, many people see, there's a lot of hype around the new science. Many people see the new science as like a market correcting itself, for example. Many people see what has been made possible by microchips and cathode ray tube screens is modeling of processes and regularities which were not previously apprehensible, if you like, purely with the use of lenses, telescopes, and microscopes. So they have this new device which allows one to actually begin to search for regularities in the world of change, as opposed to the regularities where all change was eliminated and we were really just looking at static phenomena. So what many people are beginning to say today, I'm not convinced that it's absolutely true, is that all of science, virtually since the 16th century, really was dealing with a very, very small percentage of real natural phenomena, that most of the world is essentially moving, changing, nonlinear, possibly chaotic, and certainly complex. What we are doing, perhaps, is moving technique. You see, on one level, it's great that there was all of this area which we forgot about, but all of this area of reality which was untouched by technique and by mathematics and by numericalization. In a way, what we have to lament today is the fact that that whole ecology, which remained outside of the scientific purvey, is now going to become colonized by computation and by science. But essentially, what the more optimistic people feel is that we are now able to bring our techniques of knowledge more into step, if you like, with the real processes of unfolding of nature. That's as best as I can answer it now.
Doesn't it order the disorder, or the scientific control becomes more extreme?
I think there's that certain. Well, let's put it this way. I would like to publicly suggest that I also have slight Buddhist leanings. I guess I'm the, and I am not afraid to say that at this point in time, especially after 3 other people far more important than me in the world have also said it in this very podium in the last few days. I would say that it's a hard call right now. It might make it possible to transform techniques of knowledge. Or the other possibility is simply that really what it will do, like you say, is harness and make the universe work, or actually turn it into exploitable work, if you like. So, frankly, I sit on the fence. I would like it to go one way. It annoys me that the real gung-ho, Buddhist types are just cheerleading the new sciences, because I think that they're unaware of the terrible dangers which lurk. And on the other hand, I can't bear really the types that are so allergic to the idea that knowledge might change. It did once. It did once at the other end of the revolution that's taking place today, when the mechanistic worldview was assembled. We moved from, well, even just to talk in purely architectural terms, as Cassirer, again, in his other great formulation, we moved from an aggregate space to a system space, and it's the application of mathematics to nature. I think that it's a hard call, and I think that we have to hope for both. Yeah.
Sanford, I'd like to pull together some ideas across the speakers. Peter berated the idea of architecture as frozen bugs. And, but you seem to be defending the idea of architecture as frozen complexity, or at least suggesting that it's possible. And of course, because you've said that, in effect, it's the process which is reality, which brings us to Whitehead's famous book, Process and Reality. And Whitehead is often thought to be the first postmodern philosopher, and he's the one who goes back to the Romantics and sees that is a resistance to modernity. So architecture as frozen complexity. Well, now, this is what the futurists had the problem with, and when the metabolists came along in the 60s, Tanguy was criticized by Frampton and others, and many critiques saying, well, all right, process all very well, and even Cedric Price, but when it comes down to it, it's all frozen, and it never changes. So, and then the question is, as an institution, architecture is about also stability. Now let me switch to what I hope to get from Professor Allen last night, but we didn't, and that is the stock market. Because, as you know, the notion of the stock market as a chaotic system is that there are pockets of predictability within a great sea of chaos. And it is the hope of at least Prediction Incorporated and other people to pick out what are those creos, in your terms, those places, those monuments, or frozen pieces, and to bet on them. But when you do that, what happens, and this I think what Alan was saying, is it changes the market.
Yes, well.
Right? It changes the market. But what it does, and what the point being made down here is that what they say in the economic world is that smooths out the market and makes it act more, quote, rationally. In other words, I don't know if that's true. They say it makes the market less chaotic.
No, it makes it more efficient and therefore less rational, but more random.
Well, it doesn't matter. Really what it does is it changes the scale of the regularities. It really just pushes them down smaller and smaller. And I'll tell you something, I read and reread that survey in The Economist that dealt with the new mathematics and their application to markets. And I can tell you something, the writer, for the first time I've ever in The Economist, did not understand what the heck he was talking about. But I know why. Because the people that he was talking to, who were doing this work, didn't understand what they were talking about. That we were talking about this the other night. It's still snake oil. I mean, that is one area, like looking for, in a way I'm here, I know Rob Shaw's probably shaking his head, and, I'm talking through my hat because, some of his friends, his very, luminary friends have gone off and started a company, a well-known company based on doing this type of prediction. I don't know what to say about that. I do know that it doesn't really change a thing. The market is an ecology. We also know that real random, ergodic, or stochastic processes do exist. Some people think that there may be an attractor embedded very, very deeply in market behavior. It is also possible that there isn't one. Now, are people putting their money on all these new regularities that are turning up? Well, some people are, but I think they're putting very little of their money on it. I think it's experimental, and I think it may turn out that things like markets are intractable.
One more question?
There was another
Right.
part. Yeah. Oh, by the way, I just want to say one thing. My whole career in architecture began with studying the futurists. And in many ways, all of my work in dynamics really comes out of the futurists. I would like to say one thing. My question to you the other day was because I felt that you were interested in the frozen movement. I am not. What I really want to do is really understand. I want to keep everything moving, and I want to understand architecture as a dynamic system. I do not believe in Peter's insistence that it all really comes down to frozen stuff anyway, because it doesn't. Bugs can be seen as frozen stuff if you put them if you put their exoskeletons under a microscope. I think.
Raul.
I have two questions. We've seen, thank you for a quite clear presentation of this material. You've seen that which you have described, which we've gotten to some other scientists in ways, be turned into a cute metaphor very quickly. And you've been very kind, I think. It's very nice. And I would like to ask you, why is the material that you speak about is such a good metaphor for private use? Because effectively, we've seen it being turned into a metaphor which is useful for the private decision-making process of an architect, which is not the same as an organism. Why?
Wait a minute, it's not the same?
Why is it such a good metaphor?
Now, you're saying I should try to understand your question in terms of private use.
Yeah. The second question was then. Because you have hinted several times at the seductiveness.
Yeah, and you're asking why should one allow oneself to be seduced? Because, I mean, the implications of this in private use.
Be a bit more critical about the use that you see.
Well, okay. I mean, you know, maybe this is the weak part in my position, but I think that what the significance of these ideas, though I don't really deal with private use, for private use, are essentially that one should resist all forms of mechanism in the design process. What I believe is there's a word which is very dangerous to use in schools, and I'm always being reminded of it. See, I'm a great reader of Bergson, and you know, Bergson championed a certain concept of intuition, and he believed that it was a science. And I believe that intuition is potentially a science, okay, and not a fuzzy, you know, flaky thing. Now, I like to use that word, and I always hear Bergson resonating behind it when I use the word, but that's my introduction to being able to say the word intuition here. I think that complexity is about educating intuition for the most part. I mean, I was pretty impressed, for example, in Glick's book when he talked about, you know, Rob and his friends who would sit in front of, I think it was them, sitting in front of screens watching oscilloscopes move for hours until they could develop a kind of in-syncness with those movements, as if they were educating their intuitions. Now, the one thing I know is, I don't know if you can get that from watching oscilloscopes, but you can certainly get it from watching natural processes. And there are mathematicians, for example, like René Thom, and I mean, obviously, and people like Leonardo da Vinci, who understood, who watched, if you like, the dance of forms, and understood if their underlying sort of logic through observation.
We'll return to this in the discussion.
Thank God I'm out of here, man.
Thank you.